one is Arieh Iserles to talk about approximations on the real line. When he's finished, we'll go for a short break, I think 5-10 minutes or so, and then there will be Robert McLaughlin who will talk about the algebras of classical mechanics. But first, Arieh, please.
Okay, so I'll be talking until this clock here shows 10 minutes. Okay, so approximation on the real line doesn't sound as something even remotely related to this semester, this program, but I hope to persuade you that it is. And by the way, this is joint work with Malmquist Webb, who will be actually visiting not our program, but the next parallel program in complex analysis. And everything starts from differential equations, as we know that everything starts from differential equations. And typically, many differential equations in a natural sort of way are defined in the entire space, in RD. Well, we can also define them on manifolds, so boundaryless manifolds, but let's start from RD. The only problem is that if you want to apply anything with the word finite in its title, finite differences, finite elements, finite volume methods, and so on, by definition, you have a finite number of degrees of freedom, which are distributed in space, and so you have to take your infinite space and contract it to something finite. And this has led to huge effort in applied mathematics in the last 100 years, how to do it correctly. So, for example, the Dirichlet to Neumann map, absorbing and reflecting boundary conditions, the Enquist-Maida theorem, and so on. And then many people impose, say, periodic boundary conditions, not because they should be there, but because it makes life easier. Or many people just decide that, well, the boundary is far away, who cares? And sort of collective name for them is fluid analysis. And however, there is one group of methods for which we can work in an infinite space exactly like you can work in a finite space, because although we have a finite number of variables, they are unrelated to space. And these are, or to a position within space, and these are spectral methods. So, very briefly, a single slide primer to spectral methods. So the idea is we have, say, a PDE. Think about a linear PDE, it is not necessary, but a boundary value problem given in some domain omega, which might or might not be finite, and we know that solution evolves to some friendly subset of space. And suppose that we have an orthonormal system, so we have an inner product, it is after all subset space. We have an orthonormal system typically with regard to L2 of omega, and we wish to, which is complete in L2 omega, and which is consistent with the boundary conditions. So typically we have an orthonormal system plus something, so really an affine space. Something that obeys boundary conditions plus a linear system that obeys zero boundary conditions, or things of this kind. I don't want to go in that direction because this would be irrelevant. Anyway, the idea is that we can expand every nice function in terms of this basis, and so we seek a truncated expansion in this basis. So we are seeking it. So we have n plus 1 degrees of freedom, capital N plus 1 degrees of freedom, and so we see coefficients u n hat, so that this, in some sense, is an approximation to the solution, and the sense typically is obtained using Galerkin conditions. You can proceed in different ways, but Galerkin conditions are the most obvious in this general. And note that the word bounded didn't appear in this explanation. Omega can be bounded or unbounded, doesn't matter. And given that I am, and we in this program are interested in time-evolving problems, similar situation applies. In that case. So we have an equation of this kind, and again, L is some sort of differential operator, linear or in principle non-linear, and we have some initial and boundary conditions, and we have a well-posed operator here, and again, now the U hats depend on T, and phi n's again form an orthonormal system, and we are using this sort of Galerkin conditions which need to be solved by an ODE method. So we discretize with a semi-discretize with a spectral method, and then use an ODE method to solve the system. And we have really 4 considerations here. And later we'll see that these four considerations force us into a very, very narrow path. First of all, we want stability. Stability in the sense of flux. So we want essentially all this method, as capital N tends to infinity, to be uniformly well posed. We might have structure to be preserved, and we want to preserve the structure. And later on we'll see a specific case in which the solution is norm conserving, conserves the L2 norm. So in other words, the solution is unitary, and we are keen to preserve unitarity. We want to compute everything fast. And typically when we say fast, in one dimension we mean order n log n operations. In more dimensions, in a modest number of dimensions, the scale is n to d log n. If d is very large, then of course you need extra tricks like tensor trains and spans grids, but I will not go that direction. Finally, fast computation is not enough to ensure easy computation. Typically, especially using splitting methods, we'll somehow discretize our operator, and then we'll need to evaluate the exponential of time step times our operator. And we need some efficient ways of calculating this exponential, again, very rapidly, in roughly speaking the same number of operations, and again, subject to conservation of structure. It is not good enough to spend an awful lot of computational effort, and at the end everything fails because you evaluated the exponential by a method that doesn't conserve structure. So, suppose that we have a complete orthonormal system in L, so L2, intersection of C infinity. I don't want to be bothered by whether derivatives exist or not, they all exist. And in that case, a derivative of each phi n is itself in our Hilbert space. So we can span it using elements of the basis. In other words, there exists an infinite matrix D that takes our orthonormal system to its derivatives. And this linear map is called the differentiation matrix. And there is this very important lemma whose proof takes slightly less than it takes to write it down, which is that if all the phi n's obey either zero Dirichlet conditions or periodic boundary conditions or Cauchy boundary conditions, then D is necessarily skew-Hermitian. And if you replace it by a finite section, it remains skew-Hermitian. And if everything is real, skew-symmetric. And skew-Hermicity has fantastic virtue. It ensures unitarity. An exponential of a skew-Hermitian matrix is automatically a unitary matrix. Its norm is 1, and it preserves Euclidean distance. And by the way, this sort of, as a footnote, is one interesting benefit, not well-known benefit of spectral methods. Because you can take, for example, finite difference methods, in which case it is not guaranteed the differentiation matrix will be skew-symmetric or skew-Hermitian. Not only it is not guaranteed, but in general it is not. So Ernest Heyer and I have a sequence of papers, and among other things, we start by proving that the highest order of a finite difference method on uniform grid with a skew-symmetric differentiation matrix is 2. You can go to higher orders only if you have incredibly fancy non-uniform grids, which probably make the work unrealistic, so beyond order 4. Whereas for spectral methods, essentially you can go as far as you want and you will have skew-symmetry. But now, before we go further, the example that motivated us, so based on my work with Carolina and Pranav, and other people are also working on this who take part in this program. So we have a linear Schrödinger equation in semi-classical regime, so this is the interaction potential. We have periodic boundary conditions, because everybody solves it with periodic boundary conditions. And as Ella Fitzgerald found, everybody is wrong but me. And in this case, the obvious choice in one space dimension is Fourier basis in several space dimensions. You take the tensor product of the Fourier basis, and in this case, we have stability, because the differentiation matrix is a diagonal matrix, which is skew-Hermitian, imaginary diagonal. It preserves structure. Once you are using splitting methods and various types of splitting methods, and there are now many, you can easily conserve unitarity. And unitarity here is not an optional extra. Because of the nature of the equation you are solving, you must conserve unitarity, otherwise the solution is non-physical. All the computations can be done with FFT, so it can be done fast, and using exponential splittings. Everything can be computed very rapidly, there are no commutators involved, and so on. So all this is very nice, except for the periodic boundary conditions, because they really don't. Once you are solving this equation for a long time, the solution reaches the boundary. And then if you have a periodic boundary conditions, it is like in these old-fashioned computer games in which you are flying a spaceship, you are reaching the top of the screen and you reappear from the bottom of the screen. It is not unphysical. So essentially what you need, and this happens by the way in computations, so you need to be more clever. So what I want is a skew-Hermitian differentiation matrix, but I want something else. This was item number 4. This was easy computation. I want my matrix also to be tridiagonal, because then it will be easy to compute the exponential, etc., etc. So we want tridiagonal skew-Hermitian differentiation matrices. Well, it is always good in mathematics to start your discussion by arguing that what you are doing, what you are talking about is not an empty set. So there is one example of such function which is known to many, many physicists, not really to mathematicians, but physicists know all about it, and these are Hermite functions. Not Hermite polynomials, but the relative Hermite functions. So phi n is e to minus x squared over 2 divided by this number that makes everything orthonormal times the nth Hermite polynomial. These are beautiful functions. Unlike Hermite polynomials, they are uniformly bounded. They are all less in absolute value than something 0.86 something, the Kramer inequality. And there are eigenfunctions of the Fourier operator, and there are many, many beautiful features. And in particular, they obey the derivative can be represented as a skew-symmetric function. Skew-symmetric tridiagonal function. So here we have a special case. And turns out that this is really a very special case. Matrices like this can be, or orthonormal systems like this can be characterized, and this can be done in a systematic sort of way. This is, had I been giving this talk half a year ago, this would have been the talk, but today I'll go way beyond that. So the idea is that we are seeking an orthonormal system in H1R, actually it will be in C infinity R, that obeys this, so the phi n derivative is of this kind, obeys this recurrence relation. So this is the differentiation matrix. And to be skew-Hermitian, so it is tridiagonal, and to be skew-Hermitian, we have pure imaginary elements along the diagonal. In the off-diagonal, here we have Bn, here minus Bn minus 1, which are real. Of course, instead of this, we can have complex Bn and minus the conjugate of Bn minus 1 here, but I can twist all the phi n's without loss of generality to bring them to this form, which is much, much easier to work with.
Sorry, you want them orthogonal in L2?
L2.
There's no weight function or anything?
No weight function at all.
Okay.
We can do it
These are the
also with
harmonic
weight
oscillator eigenfunctions, so they're orthogonal.
We can do it with different weight functions. We can do it in Sobolev space instead of L2, but this is for different weight. Yet to be written. Anyway, the first result, I will not go through proofs because there is no time. There exist complex numbers kappa and L that obey some simple recurrence, so that each phi n can be represented as a linear combination of phi naught derivative up to the nth derivative of phi naught. But of course, we don't know what is phi naught. Yes.
So I mean, these harmonic oscillator eigenfunctions fall off very rapidly. So I mean, if you're doing something like, say, the wave equation, what is going to happen to these pulses of waves when they get far away from the center? Will they still be resolved?
Well, if it is an L2 function, then ultimately, if it is L2 intersection with, say, C or C1.
No, I don't mean ultimately. I mean, if you're using, say,
Okay.
40 basis
Hermite
functions, how far can I get?
Hermite functions decay very rapidly.
Yeah.
But we'll see here that there is a whole continuum of functions, some of which decay much, much slower or much faster. And actually my favorite functions that we'll reach later decay geometrically, but not exponentially. Anyway, so the question is, what is phi naught? How do you determine phi naught in this case? And also you need the B naught, B1, and so on. However, something more interesting happens. So take the Fourier transform phi n's. And remember, Fourier transform takes a derivative and makes it into a product by I. And this is the magic. Very simple magic. So you multiply it by minus I to the power n to get rid of this I. You obtain functions which will be real and obey the three-term recurrence relation. And everybody remembers orthogonal polynomials obey three-term recurrence relation. What not everybody remembers is something else, which is known as the Favart theorem, to celebrate the fact that it has been proved by Bernstein, reproved by Shochat and Tamarkin, reproved by at least 20 other people until Favart proved it, which says the following. Suppose that Pn is a polynomial of, we have a sequence of polynomials, say of degree n, that obey this sort of three-term recurrence relation, where the alpha n's are non-zero and gamma n's are positive. In that case, there exists a Borel measure, not necessarily unique, by the way, with respect to which these polynomials are orthogonal. In other words, a three-term recurrence relation, in some deep sense, is not a consequence of orthogonality, it is the same as orthogonality. So, in other words, there is some Borel measure hiding under that. However, in other words, the psi n's can be orthogonal polynomials with respect to some measure. But actually more than this is true. Because suppose that we take orthogonal polynomials with this recurrence coefficients, and then multiply all these orthogonal polynomials with the same function, by function g. Then again you have this recurrence relation. We call this new function modifier. So we have this orthogonal polynomial that obeys recurrence relation, and we multiply it by some universal function g. And turns out this function g is absolutely essential here. And in this case, we have the psi n's, go back to the phi n, so multiply each one of them by I to the power n, take the inverse Fourier transform, and bingo, look what we have. We have the Plancherel theorem. The Plancherel theorem says that in L2 norm, minus infinity, distances, inner products, are unchanged by the Fourier transform. So in other words, phi n times phi m conjugate, this integral, is exactly the same as this integral. We have this constant in front, which is benign, and here we have g squared pn. But the pn's are orthogonal polynomials with respect to some measure b mu. And we want this to be orthogonal. And this tells us exactly how to choose the modifier. So in other words, if d mu, the measure of d mu, is absolutely continuous, then it has a Radon-Nikodym derivative. We can express it as a wave function times dx. The wave function is greater or equal to 0. G has to be the square root of the wave function. Bingo. Everything is orthogonal. Have we done our work? No, we haven't. It can be orthogonal, but we have no promise that it's complete. We have no promise that all of L2R can be spanned by our functions. Very easy to give counterexamples, and we'll see soon. Then, because actually, turns out that the system we just designed, in general, is not complete in L2. It is complete in what is known in harmonic analysis and signal processing as a Paley-Wiener space. The Paley-Wiener space of the interval AB is a set of all L2 intersection C functions f such that the Fourier transform is supported by the interval AB. So typically in signal processing, we want functions in Paley-Wiener space because we want functions where we are cutting off highly oscillatory high harmonics. We want band-limited functions. Here, we want to avoid band-limited functions. We want our functions to be dense in all of L2. So in other words, we want the support of the Fourier transform to be the entire real line. But what is the support of the Fourier transform? It is support of the underlying measure. In other words, we need, first of all, we need the support of d mu. If the support of d mu is the entire real line, like for Hermite polynomials, we are safe. If, for example, you are taking Legendre polynomials, and soon I'll give you exactly the functions phi n for the case of Legendre polynomials, you will not be able to recreate all of L2R. However, more is true, because suppose now that we are taking the real line, we chop it into subintervals, in a finite number of subintervals. We have different orthonormal systems in each of these intervals, and then we strip them together. So we take the Fourier transforms of each subinterval, and then we put it together. This may sound as a completely crazy procedure, but later we'll see that in one case it works like a dream. In that case, again, we have completeness because essentially we are stitching up different Paley-Wiener spaces. And this is a complete characterization. These are all orthonormal systems in L2R, which are complete in L2R. So the first example is Hermite functions, that's easy. And remember, So the modifier is e to minus x squared over 2, the square root. This explains exactly the construction. Okay, take instead the Legendre measure, standard Legendre polynomials. In that case, the phi n's are spherical Bessel functions. Very, very nice functions, but the system is not complete on the real line. They're orthogonal, surprisingly, but useless. Now, this is my favorite system. Take the interval 0 infinity and the Laguerre measure, e to minus x dx at 0 infinity. In that case, we obtain a system of functions like this, beautiful rational functions for every n greater or equal 0. There's only one problem with this system. It is not complete. You know, if you apply it to a function, you recover only the positive Fourier coefficients. The negative Fourier coefficients are lost. But you can easily fix it. Add to it the reflection of this system here in minus infinity 0. So e to x dx and minus infinity 0, stick them together, and all you need to change is remove this plus. Simply now n ranges from minus infinity to infinity, and we have this absolutely wonderful system, orthonormal. This is an orthonormal system on the real line of rational functions with a single pole at minus a half, a single 0 at 1/2, or minus half I, and it is known since 1923, or at least was implicit in simultaneous papers by Malmquist and Takenaka in 1923, but since then has been rediscovered by many people, by Norbert Wiener, by Christoph, by Boyd, by Ander Weidemann, Margit Popp, and so on. But people in harmonic analysis know what is Malmquist Takenaka. And these are wonderful functions, and they decay much slower for large values of x. Okay, and now remember, look again at this Malmquist Takenaka, because something magical happens here, which doesn't happen with the Hermite functions. Here, forget this n, the plus 1. Look only at n here and n here. We have 1 minus 2ix over 1 plus 2ix. It's a Möbius transform, which lives on the unit circle. So it equals to some e to I theta. Make this change of variables. So x equals half tan theta over 2, and the nth coefficient in the expansion is the integral from minus infinity to infinity of f times the conjugate of the n, phi n. But now, changing variables, we obtain this integral here. Minus pi to pi, 1 minus I tan theta over 2, f of these twisted coefficients, times e to minus I n theta. This is a Fourier integral. You can compute it with a single FFT. Mind you, there is a little worm hiding in this upper, which later will cause some minor, or not minor problems, which is that tan theta over 2 blows up at plus minus pi. So both here and there. But remember, f is a function which is in L2, and we can assume it is also in C infinity. So it goes to 0 very rapidly toward infinity. And the functions we're interested in go rapidly to 0 far away. So this doesn't cause problems insofar as application of FFT is concerned. They will later cause problems when it comes to analysis. And so, remember, item number 3 on our agenda was fast methods. So this gives us fast method. N log n operations, and you have the coefficients. With Hermite expand, Hermite functions becomes more complicated. Actually, there is a method using n log n squared to compute Hermite coefficients. It's based on slight cheating plus fast multiple, but can be done. Okay, so are there any other fast methods? And by fast methods, I mean n log n. Can we characterize them all? And the answer is yes. So first of all, so what have we done to obtain this? Look again in this. We had a mapping taking us from the interval from minus infinity to infinity to a finite interval. And this mapping was a monotone, strictly monotone mapping without loss of generality, strictly increasing mapping. In our case, it was half time theta. So at 0 is 0, at infinity it is plus infinity, at minus infinity is minus infinity. At pi, so plus minus pi is plus minus infinity. Now, so suppose that we have in general a strictly increasing function mapping minus pi to pi onto the entire real interval, and denote the inverse by capital H, and we seek a function capital phi, or a system of functions phi n. Remember, capital phi is phi n. Orthonormal functions such that f n hat, which is the integral of f and phi n. So it is the integral of f and phi n conjugate. So it is some constant gamma n conjugate times integral from minus pi pi of f with our mapping times some kernel times e to minus I n theta. So exactly what we said. Constant, this is the kernel, this is the mapping, but with greater generality. And in that case, phi n is, taking conjugate, is gamma n, is some kernel capital K of x, e to I n capital H, again I'm removing the conjugate. So can we characterize all such systems? And the answer is yes. Again, I will not go through the proof, but preprint is available on demand. And turns out that there is exactly one such system. And this is what we call generalized Malmquist Takenaka. So we need to take a number lambda, which is complex but is not real. And two real numbers, theta and tau and delta, and numbers gamma, complex numbers which are all of modulus 1, and then phi n is gamma n times square root of the absolute value of imaginary part of lambda divided by pi, e to I tau x times this, x lambda minus x to the power n plus delta over the conjugate of lambda. Remember, lambda has the non-zero real part, so it is non-trivial to conjugate, minus x to the power n plus delta plus 1. For Malmquist Takenaka, tau is 0, delta is 0, and lambda is half, or minus half I. And if we normalize gamma n as minus I to the power n, we have this tridiagonal skew-symmetric, skew-Hermitian differentiation matrix with the bn's and cn's as given here. So, in a sense, the real part of lambda, the non-zero real part of lambda, corresponds to a shift, whereas tau corresponds to a twist of the solution. And one of open problems here is how to choose a good twist and a good shift for any particular function.
Sorry, on the previous slide, there's the delta, that's sort of like throwing away the first members of your family.
Yes, so,
Yeah.
yes. Or shifting them, because if you are taking delta equal to 1, it is like shifting the entire system where you are not. Because remember, the sum is from minus infinity to infinity.
Oh, it's minus, okay.
Yes.
So, yeah, there's no.
Yes. But, so this is the only possibility of getting a skew-Hermitian tridiagonal differentiation matrix plus computation using FFT. But FFT is not the only fast method. We have two other fast methods, fast cosine transform and fast sine transform. And they allow us to use skew-symmetric matrices. So here is an example. Set phi naught equal to 1 over square root of pi times 1 over square root of cosh x, and otherwise phi n's defined in this manner here with Chebyshev polynomial here of tanh x. So the only difference is if you set here n equal to 0, you need to divide by 1/2. And in this case, this phi n's obey this differentiation matrix. And we obtain them, essentially, we can obtain them by mapping everything, as we'll see later. Okay, so setting x equal arc tanh of t, making this change of variables, we obtain this integral here. And this integral can be obtained by a fast cosine transform. Well, there are several different fast cosine transforms, but it is fast cosine transform 2 to be exact. That doesn't matter. And by the way, in case you are interested, what is the underlying Borel measure? It is quite a complicated one. It is the absolute value of the fourth power of the absolute value of the gamma function of half I psi. It was not easy finding it, and we have a more general result. Anyway, so this is an example. Things like this exist. Can we characterize them all? And the answer is proceed as before. But now we want everything is real, so we have a skew-symmetric function, so which is tridiagonal, and Fn hat, there's no conjugation, so we are seeking a strictly monotone function mapping -1, 1 to the real line, and d small w, which is capital W dt, is absolutely continuous. And turns out that all such systems can be characterized. Essentially, they are tanh-Jacobi systems, or arc-tanh-Jacobi systems. So Pn is a Jacobi polynomial, alpha and beta are greater than -1. Gn is some nasty coefficient that makes everything orthonormal. And otherwise, we have here this weight function times Pn. In particular, well, now, it is possible to compute coefficients for all types of Jacobi polynomials using various clever methods in n log n square operations. There are several methods. Probably the best method is at the moment by Nick Hale and Alex Townsend, the newest one. But in 4 cases, 4 choices of alpha and beta, we can do it in n log n, easily. And these are the 4 Chebyshev polynomials. So everybody is familiar with the Chebyshev polynomial of the first kind. So Tn of cos theta is cosine theta. This is the weight function. Many people are familiar with Chebyshev polynomials of the second kind. There are also third and fourth kinds. And between them, these are the 4 choices in which, in the first and the fourth case, we can use fast cosine transform. In the second and the third case, we can use fast sine transform. And all this works. And then we can go one step further. Because, it is, okay, instead of doing it from -infinity to infinity, take your function f, divide it into an odd and even part. And then everything reduces to the interval 0, infinity. So Fe is the average of fx and f minus x, fo is fx minus f minus x divided by 2. And then our coefficients are given here using even functions and odd functions. And now we can change variables separately here and here using two different measures. So the same monotone mapping, but two different measures. And again, we can characterize all such functions. And turns out that in that case, necessarily, our mapping is no longer arctange. It is 1 minus 2 over cosh squared x. And these are all possible choices for every alpha greater than -1. So when alpha equals 1/2 or equals -1/2, we will cover again Chebyshev polynomials, otherwise we don't. And we'll cover some very special cases here. In one particular case, for example, we'll cover polynomials due to Karlitz and so on. So, and this more or less exhausts all the list of fast transforms. So now let me move in the last 10 minutes to essentially a virgin territory. How do we approximate on the real line? So there is classical approximation, and it exists for more than 100 years, started from the work of Bernstein and many other people later. You can find it even in textbooks. So suppose that we have orthonormal system in a finite interval without loss of generality -1, and all the phi n's are analytic in the interval and slightly outside the interval, and we take a function f, which is also analytic in the interval and slightly outside the interval. What I mean by slightly? So denote by C bar the Riemann sphere. dRa is the disk of radius r centered at some complex point A, and define A rho is this complex number, pure imaginary number, and R is this real number, R rho. And if we can extend F to this ellipse, this is an ellipse if you look carefully, which is the Riemann sphere minus the union of these two circles. In that case, Fn hat decays. So radius rho. Okay, so the decay, if we can extend it to this, then it decays like 1 over rho to n. So we have geometric decay of the recurrence coefficients, in other words, geometric convergence. In particular, when rho is greater than 1. And the only problem is that this doesn't work at -infinity. So, and here is the example that I hope will make you sit and watch exactly like it did it to me. Take the Malmquist Takenaka system again, and take this nice function 1 over 1 plus x squared. So the function is analytic on the real line. It is meromorphic, has poles at plus minus I. And I can write down explicitly its expansion in Malmquist Takenaka functions. Here is the expansion. Everything decays like 1 over 3 to the power n. Wonderful. So rho is 3, and we have lightningly fast convergence. Okay, so you say, first of all, you say, show me. Here it is. 10 terms, 20, 30, 40. So for 10 terms, we have 0.00001. For 20 terms, we have 10 to minus 20. For 40 terms, 10 to minus 20. Very, very rapid convergence. In case you think that the Hermite functions are competitive, these are exactly the same results for Hermite functions, the same number of terms, and the decay is very, very slow. Compare 5 times 10 to minus 20 compared to 0.0012. Hermite functions are really non-compatible in this case. However, now make one single amendment. Instead of 1 over 1 plus x squared, write sine of x over 1 plus x squared. Now, Sine x, entire function, bounded on the real line in absolute value by 1. What can go wrong? This is the outcome. This is the error. 0.02, and for 40 terms, 0.007. Well, it is not permission to kill, it is permission to give that error. What's going on? Why the sine x destroyed everything? And the answer is, because in that case, we cannot extend everything. Even if you are taking the definition of this Bernstein ellipse and you extend it to a Riemann sphere, so you do it around infinity, you cannot do it with sine x over 1 plus x. So you can do it with this function, not with that function, because sine x has essential singularity at plus minus infinity. Because plus minus infinity is the north pole of the Riemann sphere. So nothing works in that case. And for Hermite functions, nothing works almost by definition. Because for Hermite functions, e to minus x squared over 2 has even worse essential singularity, and it is built into a function. Even for 1 over 1 plus x squared, you'll have essential singularity. Does it mean that geometric convergence is impossible? Nobody knows. We know a little bit, very little, but, and numerical results in various cases that interest us are very, very impressive actually. But what can we do? So essentially all we can do is an ad hoc method, which is steepest descent. The problem with steepest descent is that for every function you need to do it separately. So essentially the idea of steepest descent that goes back more than 100 years, back to Stokes and so on, and Cauchy actually, so almost 200 years. So suppose that we have a function analytic in some domain. We have 2 distinct points A and B in omega. We take the integral from A to B of f z dz. Then, of course, we can perform this integral along any Jordan curve joining A and B. And the integral will be the same. And now the trick is to choose a curve of so-called steepest descent in which we can approximate f by an exponential of a quadratic function that goes through a saddle point. And this really has to be done separately for every function f, except there is some work of Philippe Flageolet and Bruno Salvi that does more general functions using symbolic algebra. So it can be done, but even then it is 20% symbolic algebra and 80% elbow grease by a human, in my experience, but can be done. So, Andre Weidemann evaluated this function, this speed of decay for a bunch of functions. So 1 over 1 over plus x to 4, geometric decay. Rho is no longer 3, it is square root of 2 plus 1, but still very impressive. E to minus x squared, geometric speed of decay. No, not geometric, it is sub-exponential, but almost exponential. E to minus 3 halves, all this from Malmquist Takenaka, times mod n to power 2/7. So it is still what is called spectral, faster than 1 over the polynomial. The same for 1 over cosh. Slower, but still super polynomial. Sine x over 1 plus x squared is big O of 1 over n to 5/4. Very, very disappointing. Sine x over 1 plus x to 4, slightly faster, but still not terribly usable. And nobody has the faintest idea what is the general pattern. It is a wide open problem. And perhaps I will finish very, very briefly. So let me go back to the very beginning, and our motivation was solving the Schrödinger equation and in general dispersive equations of quantum mechanics. And this dispersive equations have the feature that the solutions are linear combinations of wave packets. And this has deep quantum mechanical meaning. So a wave packet in one dimension is something that decays super exponentially times something that oscillates fast. And we have a linear combination, unknown linear combination, so things of this kind. And absolute value square of that, in general, it's a complex valued functions. Absolute value square is a probability function. That's why you are forbidden to forego unitarity. Unitarity is really essential. And we already have a theory that more or less shows how fast these functions decay using these different systems on the real line, Malmquist Takenaka, generalized Malmquist Takenaka, Hermite functions, and Fourier expansions in a very large box. And Malmquist Takenaka wins, but this is again for another talk. So here are examples: e to minus x squared cos 10x for 10, 40, 1700 coefficients. So this is Malmquist Takenaka, and these are the errors. And this is Hermite. And you can see here that the error, it is respectable, but not as good. And in general, the larger you take this number, the more Malmquist Takenaka wins. So that's it. Thank you for your attention.
Thank you, Arieh. We have some type of question.
Plenty of time.
Thank you, Arieh. So this is just a comment. At the beginning, you said the Fourier differentiation matrix was skew-Hermitian. That's because of the basis you wrote it in. If you wrote it in real space, then it wouldn't be symmetric. You'd need to adapt the inner product as well to keep track of that. So I think if in your construction, if you also allow the matrices to be antisymmetric with respect to some inner product that you determine, that's the matrix, tridiagonal matrix, then you might find more families of functions.
I think that this is actually tight. So if you're willing to forego tridiagonality, then obviously there are many more things, and we have examples. But as long as you want tridiagonal, you want this particular recurrence relation, say skew-symmetric.
Yeah, no, that's my point.
Yeah.
If you make it not be skew-symmetric, but
Skew-Hermitian.
skew-Hermitian with respect to some other inner product that you also determine, then you may find more.
Skew-Hermitian is still with respect to L2.
Yeah.
If you make it with respect to a different inner product, as I said, we can characterize this as well. So any L2 in R, inner product, so if you are throwing in a weight function, we can characterize it, and it is obvious how to do it, because the modifier has to be changed. Each time you want to exploit orthogonality in the Fourier space. So all you need is to change the modifier to get the right wave function. And what is nice is that you can do it also with Sobolev measures, not only with Fourier measures.
So, I mean, if you take your favorite basis and you're using it to simulate Schrodinger equation, but now, we're not going to, go to an infinite number of modes because you only have a finite number of modes. So, I mean, what happens at late time? I mean, the wave packet is going to spread out. Is there going to come a time where your finite number of basis elements no longer well resolves this, or do you have some sneaky basis where this doesn't happen?
Well, we still have to taste this pudding. In other words, it hasn't been implemented. However, my guess is that this probably will persist for much longer than the Born-Oppenheimer adiabatic approximation. So in other words, as long as the equation makes sense, this will make sense.
Okay, let's thank the speaker once again.